Pretty much all of our rates of change questions so far has involved differentiation, finding the rates, things like that. But of course, we could use integration to solve problems as well. That will allow us to get the actual quantity that we started off with. If we know the rate of change, we can get a formula for the actual quantity. So here is this one. So the rate at which water flows, dV to t, is that lovely expression there. We want to know the amount of water, so the actual quantity, not the rate of change, but the quantity of water in the tank after 10 seconds. And they've given me that dV to t is 2t on 1 plus t squared. Now this is where this idea of separation of variables I talked about before, and we'll see later in differential equations, becomes very useful, because what we'll do is we'll separate the variables and then match the limits up. We don't have to worry about finding constants, and we can solve this quite quickly. So we end up with the integral of dV is equal to the integral of 2t on 1 plus t squared to t. They've told me that, well, the tank's empty, so when t equals 0, v is 0. We want to know what v is when t equals 10. Left hand side, I've got that classic dV going from 0 to v, so straight away I can say that's v. Right hand side, I've got to do a bit of work. Now, v equals the log of 101 on 1. Oh, by the way, you'll notice I didn't bother going straight to v, or I sort of did, but I put the limits on at 0 to v. But that's what I mean. You don't really need to do that, because when it's 0 to the thing you're substituting in anyway, you're obviously going to get that. So v is log 101 on 1, so log 101. So log 101 litres, however big that is, I'm not sure, we'd have to work that out. 2010, acceleration of a particle, it's a trig function, so must be simple harmonic motion, I guess, where x displacement's in metres. We're giving us initial one. When does a particle first come to rest? Right, well, acceleration is dv dt. Separate out my variables then, because I basically want to find when v is 0. Integral of dv going from 1 to 0 will be 4 times the integral of cos 2t going from 0 to t. Well, in this case, it's not going to just be v, you'll notice, because 0 is on the top, 1's on the bottom. So negative 1 is equal to 2 sine 2t. We want to know what t is. 7 pi on 12, remember, got to be radians for this to work. So after 7 pi on 12 seconds, try this one. A spherical raindrop, which is kind of handy because we've got a formula for a sphere, makes life a little bit easier. Radius r loses water through evaporation. The rate of change they've given us, t's in seconds. A is the surface area of the raindrop. First thing, show dr dt is a constant. Dr dt is what we want to work out. We've been given dv dt. Can I link volume and radius? Well, yeah, I can. Volume's 4/3 pi r cubed. So dv dr is 4 pi r squared. 4 pi r squared is the formula for surface area. So that's A. They told me A was the surface area. So I can just, bang, jump straight to A. Now, remember we're trying to show that dr dt is a constant. So dr dt is, subbing in now into our formula that we've got there, A eliminates, and we end up with a constant minus 10 to the power of negative 4. So yes, the radius does decrease at that constant rate. How long does it take for a raindrop of this volume, 10 to the negative 6 meters cubed, to completely evaporate? Dr dt we now know. Volume. Yeah, the numbers are not nice on this one because of this 10 to the negative 6. So volume 4/3 pi r cubed, we want to know what the radius is. Turns out to be the cube root of 3 times 10 to the negative 6 over 4 pi. I've left it as an exact answer. Probably a lot of people just went and used an approximation at this stage. Okay, separate out the variables. Isn't this a fun little integral, right? So the lower value is the cube root of 3 times 10 to the negative 6 over 4 pi, and we're going to 0. Time, there's the classic 0 to t. So t will equal 10 to the power of 4 times r. Notice I've changed the negative, so I've flipped the limits. 0's on the bottom now, cube root of all that stuff is now on the top. And when we punch that all, we end up with 62 seconds. So 62 seconds we get. So that's how long it takes to evaporate. 9. We'll add that to our collection of questions.